Okay. Ridge regression. In linear regression, we are trying to find an intercept and a set of coefficients that minimize the residual sum of squares. The residual sum of squares is this yi minus beta 0, which is the intercept, minus the predictors for the ith observation. So the first predictor of the ith observation, the second predictor, so this is xij is the ith row and the jth column in the design matrix in X. And then we have beta j. Okay, so that's linear regression. Simple, multiple linear regression. Now in the homework assignment, you saw that if the number of predictors is larger than the number of observations, then this problem has infinitely many solutions. These solutions can be contradictory. They can tell contradictory stories. Now, one way to resolve this problem is to limit the search space, the space of possible betas. We can limit that. We can say that you are only allowed to look to find the best beta that live in this set. What is this set? The set of betas where the sum of squares of these betas is bounded by some t. And t is a number, is a knob in our hands. Obviously, if t is very large, it's as if it doesn't exist. If t is infinity, then this constraint is redundant. If t is big, this constraint is redundant and we are back to linear regression. But as we make t smaller and smaller, this constraint will become more important and it will change the betas from linear regression. And the way it will change it, in a way, it is bounding the intensity of the betas. It is bounding the intensity of the betas. This is called L2 norm regularization. Why L2? Because this is the L2 norm squared of beta, the vector beta. This is a hypersphere. This is a hypersphere, and we are saying that the beta j's cannot be very far from 0. If t is 0, then the betas are close to 0 or 0, and we are left with an intercept, a simple model. We are left with an intercept, a simple model, the simplest model possible. So if t is 0, then we only get an intercept. If t is infinity, we get linear regression if we can find an answer. And in between, we have something between these two, and we can decide how far we want to go towards linear regression, or how close we want to get to zero by playing with t. So this is called regularization, this thing here. So it's an optimization problem subject to this constraint. And this is called ridge regression. In a matrix vector format, you can just write this as the vector y minus beta 0, which is just a scalar. So beta 0 is a scalar. This 1 is a vector is an n-dimensional vector filled with just ones. And then we have our x beta. X is a matrix, beta is a vector. And we want to solve this optimization problem subject to this constraint where the L2 norm squared is bounded by t. T is also sometimes referred to as a kind of budget. The larger P, the more complex the model. The smaller the T, the simpler the model. In general, something as a side note, it's about standardizing the predictors. Okay, so there are a couple of things. One is standardizing the predictors, which means we remove the mean. And then we make sure we scale the predictor such that the variance is 1. So by doing these two things, by centering and scaling them, we are essentially saying that all the values in our X matrix are around 0, between -2 and +2, or -3 and +3. So all the numbers there are more or less in that range by rescaling and centering them. Now, why do we do this? There are two reasons of why we would do it, and there is one reason why we wouldn't want to do it. The reason we would want to do it is for numerical stability. And that becomes more important in large problems, okay? But if the range of the values in our X matrix are radically different, if you have columns that are in the millions or in the billions, and then you have columns that are in the 1,000s or 1/10,000s, then you are creating a lot of numerical instability, because then the computer needs to work within that range, and that's can lead to problems, large problems. So, but once you standardize and center them, all of them are more or less around 0 ± -3. Okay. The other reason why we would standardize is that when we get the coefficients, the size of the coefficients is going to be reflective of how important that coefficient is, that predictor is, that corresponding predictor is. Because if the predictors are in different scales, then obviously the coefficients will be in different scales. And if the coefficients are in different scales, then it's impossible to compare the coefficients to each other. So if we care about comparing the importance of different predictors relative to each other, then standardizing is one reason. Then standardizing is one way to do it. Okay, you standardize, and then the coefficients you get are naturally comparable. Now, if you don't standardize it, then it becomes a little bit more tricky to compare the coefficients. But now let me tell you a reason why you wouldn't want to standardize or scale. This is particularly important when the predictors have scales that we care. They are in a unit that we care. They are in dollars, they are in Fahrenheit, they're in Celsius, they're in whatever care, and then the coefficient that we estimate will have a very specific meaning that is tied to the scale. Centering out the values of y, you can do it, especially if there are very large numbers. It's reasonable. It's like dealing with the intercept. It's like removing the intercept. Okay. So it's coming back to ridge regression. In ridge regression, this is wrong. Should be constrained. That's what I meant. Problem. So we are trying to find the beta that minimizes the residual sum of square subject to this constraint. This is a convex optimization problem. This is a convex function, meaning that it has a ball shape. If you get to the bottom of the ball, you know that it's the lowest point of the ball. Ball shaped. U-shaped. A U, if you're at the bottom of it, you know it's the minimum. But if it's a W, then you may not know. One of the U's might be lower than the other one, if it's a handwritten W. And this constraint is also a convex set. It is a hypersphere. We're saying that the beta should be in a hypersphere centered at 0. Now it is possible to rewrite this optimization problem in a Lagrangian form, which is just minimizing the residual sum of square subject to a penalty. This penalty here, so one way to look at this lambda here is a free parameter. It's positive, always positive, and it's a free parameter. And it's related to t. There's a one-to-one correspondence between t and lambda, meaning that for every t, there is a lambda, so that these two beta hats are the same. Or for any lambda, any positive lambda, there is a t, such that these two beta hats are the same. So if t is infinity, then this constraint is redundant and we are back to linear regression. If lambda is 0, then this term is not present and we are back to linear regression. So t infinity corresponds to lambda 0, or lambda 0 corresponds to t infinity. Now if t is infinity 0, then beta must be 0, and we end up with just an intercept. Here, I just wanted to, a subtle note. Here I have introduced the intercept separately, but we learned that the intercept can become a column of x. So I just, for the simplicity of notation, I just removed the intercept. Now if lambda is infinity, if lambda is large, essentially look at this. Lambda is telling us how much the residual sum of square is important in comparison to the L2 norm of beta. This is the training error, and this is a measure of complexity. The larger the length of beta, the greater the complexity, because it means that we have a larger model space. So if lambda is large, the cost of having a non-zero beta increases. If lambda is infinity, then the only solution here is beta 0. If lambda is very large, then beta must be 0. So the larger the lambda, the smaller the beta for all the coefficients, more or less. If lambda is infinity, lambda infinity is equivalent to t0. It's equivalent to t0. Okay. The same way that we can have a linear regression with an L2 norm constraint, we can have a linear regression with an L1 norm constraint. It's called L1 norm regularization, or also lasso. Okay. Actually, I'm not looking for this paper. This paper, which has been cited 38,000 times since '96. The lasso minimizes the residual sum of squares subject to the sum of the absolute value of the coefficients being less than a constant. This is the constant. The sum of the absolute values of the coefficients is the L1 norm of beta. Because of the nature of this constraint, it tends to produce some coefficients that are exactly zero, meaning that the answer, this beta hat, because of this L1 constraint, because this is the sum of the absolute values, this beta hat, obviously depending on what t is and what x is and what y is, but in general, this beta hat tends to have zeros, exactly zeros, meaning that some of the coefficients are set to zero. And hence gives interpretable models. What it means is that it does some sort of variable selection. Even if you have many predictors, it selects the variables, and then you're dealing with a smaller number of variables which you can interpret the results. The data we studied showed how much of a problem that can be when you have many predictors. So, for simulation studies suggest that lasso enjoys some of the favorable properties of both subset selection, which was computationally very hard. So it does subset selection, and also the ridge regression. It produces interpretable models like subset selection and exhibits the stability of ridge regression. Okay, so let's skip that, but what I want to finally say, what does lasso mean? Least absolute shrinkage and selection operator. So there are two things happening. Remember these two words: shrinkage and selection. What it means is that in generally it shrinks the coefficients towards zero. So there's a bias. The bias is that, yes, there's a bias that most coefficients are zero, and those that are not zero are not very far from zero. That's the bias when you do lasso. Now the Lagrangian form is, instead of a constraint, we just add this. We just add it to the residual sum of squares. If t is 0, beta must be 0. If lambda is 0, beta is the linear regression estimate. If t is infinity, this beta is the linear regression estimate. So t infinity corresponds to lambda 0, t0 corresponds to lambda infinity. there is a one-to-one corresponding value of lambda that yields the same solution for the Lagrangian form.